Hi, this is Mrs. LaBarbera. This is Physics Chapter 11, Wave Phenomenon, Video 1. Today's topic is boundary behavior. The objectives are: know waves that encounter new mediums are partly reflected and partly transmitted. Both reflected and transmitted wave have the same frequency. Understand, for a transverse wave such as light, both wavelength and wave speed is less in denser medium. For longitudinal waves, such as sound, both wavelength and wave speed is more in denser medium. Understand waves reflected at a fixed end inverts its direction of their amplitude. On the other hand, waves reflected at a free point do not change direction of their amplitude. Reflection, transmission of a wave at a boundary. So this animation shows as a pulse comes to a boundary, part of it is reflected and part of it is transmitted. Waves that encounter new mediums are partly reflected and partly transmitted. You need to remember that both reflected and transmitted waves have the same frequency. Reflected wave have the same frequency and the same speed as the incident wave. That is because the reflected wave is traveling in the same medium as the incident wave. Since both frequency and speed are the same, so the reflected wave must have the same wavelength. On the other hand, a transmitted wave will have a different speed as the incident wave because the two mediums are different. Therefore, its wavelength must be different as well, since frequency is the same. Reflection at a fixed end. What is a fixed end? Fixed end is a point that does not move. When a wave travels along a rope and reaches a fixed end, the last particle of the rope will be unable to move while disturbance reaches it. So what happens to the disturbance? The disturbance which return to the left after bouncing off the pole is known as reflected pulse, and it will reflect downward. It's because this point doesn't move, it kind of pushes the other point downward. So the disturbance will return to the left as reflected wave, and portion will be transmitted to this point. And so this point is going to vibrate a little bit. The reflected pulse is inverted because Newton's third law of action-reaction. The rope is exerting a force upward on the pole, and the pole is exerting a force downward to the rope. The speed of reflected wave has to be the same because they have the same. Reflected is traveling in the same medium as the incident wave. Every particle within the rope will have the same frequency because they are connected to one another. The amplitude of reflected wave usually is less because energy is lost due to air resistance. Now let's take a look at a reflection at a free end. Free end means the point at the end actually moves. The last particle of the rope will be able to move up or down. So what is the characteristics of this reflected wave? The reflected wave will have the same direction as the incident waves. The only difference between this and at a fixed point is the reflected pulse is not inverted. Everything else is the same, have the same speed, same frequency, and amplitude should be a little bit less in reality. This is an ideal situation. It says there is no damping, but we know damping occurs because of the air resistance. Now let's take a look at a transmitted pulse. So transmission of a pulse across a boundary from less dense to denser. So this rope is lighter and transmitted to a heavier rope. So that's a denser medium. So reflect pulse will be inverted because this pulse is heavier, kind of pushing it down. During the interaction between the two media at a boundary, the first particle of the denser medium overpowers the smaller mass of the last particle of less dense medium. This causes an upward displacement pulse to become downward displaced pulse. So denser medium, on the other hand, was at rest prior to interaction. So the first particle of this medium receives an upward pull when incident pulse reaches the boundary. So this upward pull causes an upward displacement. So for this reason, the transmitted pulse is not inverted. Only the reflected pulse is inverted. So in fact, transmitted pulse can never be inverted. Let's seek some characteristics for reflected and transmitted. For transmitted, it travels at a slower speed than the incident pulse. So the transmitted pulse, because the medium is denser, so its speed is less. Frequency are always the same as the source, whatever produced that pulse. Because the speed is slower, frequency is the same, so wavelength has to be small because the wave equation V equals F times lambda. Now its amplitude will be smaller because even there is no air resistance, because it's harder to lift heavier rope. Now let's talk about a reflected pulse. Reflected pulse is inverted, right? The speed has to be the same because they have the same medium as the incident. The wavelength has to be the same. Frequency has to be the same. We know amplitude is smaller because the energy, amplitude represents energy. Part of energy is transmitted, so reflected has to be smaller. We can explain why this happens. So transverse wave always travels faster in least dense medium. Thus, transmitted wave will be traveling slower than the incident pulse. Since transmitted pulse was introduced into a denser medium by the vibration of the particle in less dense medium, they must vibrate in the same frequency. Since the wavelength of the wave depends on the frequency and the speed, the transmitted wave has a slower speed and smaller wavelength. Finally, the incident and reflected pulse share the same medium, so they will have the same speed. Since reflected pulse was created by the vibration of the incident pulse, so they must have the same frequency. So remember, the frequency is the same as the source. In this case, source is the incident wave. So both transmitted and reflected wave have the same frequency as the incident wave. And two waves with the same speed and same frequency must have the same wavelength. Now let's take a look at transmission of a pulse across a boundary from a denser to less dense medium. So in this case, the transmitted pulse is not inverted. As a matter of fact, it's never inverted. Transmitted pulse is never inverted. It travels faster than the incident pulse because its medium is less dense. It has the same frequency because the source is as the incident wave, but it has a larger wavelength. That is because its speed is bigger. Remember, wave speed equals frequency times wavelength. Since wave speed increased, frequency remains the same, wavelength has to increase. Now let's talk about reflected pulse. Reflected pulse is not inverted. It has the same speed as the incident pulse because it has the same medium as the incident pulse, and the frequency has to be the same because the frequency must be the same as the incident, as the source, right? And because speed and frequency are the same, the wavelength has to be the same. So boundary behavior summary. So the wave speed is always greatest in the least dense medium. The wavelength is always greatest in the least dense medium. The frequency are not altered by crossing the boundary because frequency is the same as the source. Now the reflected pulse is inverted when the wave in the less dense travel to denser medium. So, but when the reflected wave is not inverted if it's traveling from denser to less dense medium. Now the amplitude is always greater than the amplitude of the reflected pulse. So that means the amplitude of the incident pulse is always greater than the reflected pulse. That's kind of like common sense because reflected always lose some energy. Now here is the alert. This animation is showing about sound waves. Sound wave is a little bit opposite. Since a sound wave is a longitudinal mechanical wave, it depends on particle-particle interaction to transmit energy. So sound actually travels faster in denser medium. As you can see from this animation, it travels faster in solid, fastest, and travels a little bit slower in liquid, travel the slowest in gas, because the particles in gas are much further apart, so there is less interaction. Here is an example. As a light wave travels from air to water, what happens to its speed? Light wave is transverse wave. Transverse wave travels slower in denser medium. So in this case, water is denser, so its speed is going to decrease. Now, on the other hand, sound wave is a longitudinal wave. It depends on particle and particle interaction. So the denser the medium, the faster it's going to have. So for sound wave, is going to travel faster in water. That's it for today. Thanks for watching.